Alright, so we're going to kind of like take some ideas we've talked about and just tie them all together here. So we've talked about pH, we've talked about, acid equilibriums for, weak acids, and Ka and all of that. And so now we're just gonna work through it numerically. And so what this is going to boil down to, I mean, this is exactly what we're doing. I can say it in one sentence. We're just going to use an ice table, and we're going to use that to find our concentration of H3O plus, and then we're just going to calculate pH. So, that's all we're doing. That's it. No big deal. You've been doing ice tables for days. And so here we go. Let's just do an example problem. So this sentence is about to be expanded upon greatly. Alright, so first off, you have to have a question, right? We got to answer a question. So, what is the pH? That's not bad. Of a 0.250 molar acetic acid solution. Okay, well, also, Ka is given to us. 1.8 times 10 to the minus 5. Okay. That's everything we need to solve this problem. So we start out with a solution as initially 0.250 molar acetic acid. No acetate, none of that. Okay, not bad, not bad. And so let's get to work. Alright, so acetic acid, as you'll remember, was CH3 COOH. I'm too lazy to come up with multiple examples. Why bother, right? Like, we can do so much with one weak acid. So here we go. Plus H2O. You get an equilibrium. We get acetate and hydronium, both of which are aqueous. Okay, so we've got our equilibrium expression. So let's work on the ice table. Let's see here. So 0.250. Don't need that because it's a liquid. 0 and 0. Now I always wonder if I should say this or not. So when I was a general chemistry student, I would be like, this isn't 0. This is 10 to the minus 7. What do we do? What? That's not 0. Yeah, well, it's about 0, okay? Like, you could do that. You could be like, well, water always has H3O plus, like there is a concentration. We're just rounding for convenience here, okay? So look at this. We're going to go to the tenths, hundredths, thousandths place. 10 to the minus 3. This thing is, 10 to the minus 7 is 10,000 times smaller than that. It's well beyond a rounding error. It's just not going to have an effect on our answer because we have so much of this. So we're just not going to worry about it. We're just going to call it 0. And if that thought hadn't popped into your mind, you can just erase everything I said. Okay? It's one of those things. Like, now, if this went far enough, yeah. If it was a really, 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 really dilute solution of acetic acid or another weak acid, I would have to worry about how much H3O plus I started with. But because it's not very dilute, it's not on the order of 10 to the minus 7, I don't have to worry about it. Not a problem, alright? So I'm just going to call it 0 and keep things simple. My change, I'm going to shift right, so minus x, again, nothing here, plus x, and plus x. And so at equilibrium, I have 0.250 minus x will be my concentration for acetic acid. X will be my concentration for acetate and also for hydronium. Okay, and now I write my expression for Ka. Right, so this is just like last week. Yeah, a little different here. I just write Ka instead of like Keq or Kc or something. Not the end of the world. And so what have I got? I've got this times this divided by this. Alright, so CH3 COO minus H3O plus divided by concentration of CH3 COOH. sub in my equilibrium values, I get x squared up here, x times x, over 0.250 minus x, and that's equal to 1.8 times 10 to the minus 5. Okay, and so this is what we focus in on. Guess what I'm going to do here? Do you see what I can do? I can do an approximation. So you could do the whole quadratic formula, ax squared plus bx plus c equals 0, yada yada yada. Or x is small. Look at that. It's going to be a very small shift to the right. And that shift is going to be small with respect to 0.250. I'm going to bet my reputation on it. And so that means that x squared over 0.250 equals 1.8 times 10 to the minus 5. I get to ignore this x, right? I just say that's 0.250. So 0.250 minus some really small number is still 0.250. And then I solve this and I get x equals 0.00212, which is less than 1% of 0.250. I'm leaving it. Calling it good. Alright, so now what do I do? Alright, so need some more space here. That means that my concentration of H3O plus, that's equal to X, which is the following. Okay, well, I need to calculate pH. Which is the negative log of that concentration of H3O plus. So it is negative log of 0.00212, which gives me a 2.7. Does that number seem reasonable? What do you think? We've got a weak acid equilibrium. Does a pH of 2.7, does that seem reasonable? Yeah, I think so. Okay, so all you can really say here is, like, I don't know, you know, if you get like a 4 instead of a 2.7, like, yeah, okay, like you made a mistake, but it's not obvious. But if we had something like 10, if it went over 7, we would be in trouble, right? So this is an acidic pH. Okay, that makes sense. All right, that's kind of, you know, does your answer make sense? You always want to take a little bit of time and just go like, does that seem reasonable? And it might be the answer, but it might not seem reasonable to you, in which case you can learn from it, and you can kind of recalibrate what seems reasonable. But basically, we're just like, it's less than 7. Good enough, all right? Like, I could run it again, do all the numbers, make sure I didn't make a math error, but there's nothing egregious here. So we got an acidic pH. All right, so bonus question. What is the percent ionization? What's percent ionization here? Well, let's look at our formula. We'll have our equilibrium concentration of H3O plus divided by our initial concentration of HA, which is CH3COOH, times 100%. And so what this comes out to be, there's our equilibrium concentration for H3O plus, so 0.00212. We started with 0.250 molar CH3COOH, right? Like that was right here. What is the pH of that concentration of acetic acid? So that's our initial. Multiply that by 100%. And we get 0.848%. So less than 1% of our acetic acid molecules dissociate and make H3O plus. So that's what weak acids do. Just a little bit, usually. Only a little bit. Alright, so that would be how we do a percent ionization calculation. So if we were asked for the percent ionization up front, and we didn't have the ice table done already, we would have to solve it for x, plug it in here, and have at it. Alright, so that's it. You know, that's the process, right? So again, we assume just everything over here, and I'm not going to mess with you. I'm not going to give you super dilute acetic acid solutions, or weak acid solutions. But be aware that if you did, that's when you'd have to account for the fact that there actually is a teensy weensy little bit of H3O plus in water at all times. But when it's like compared to 0.250, it's zero, right? It's like you've got 37 cents in your bank account and you just got hit with like a $150,000 bill to pay. You're like, well, I do have 37. That's not really going to factor into the math, right? Like, so that's what we're doing here. Like that 10 to the minus 7, it's just not going to factor into the math. It's nowhere near the same level. So, we'll do one more video this week. Basically, we're going to run through this exact same process with a weak base. There's a little twist to get to pH from a weak base. So it's almost identical, but you'll see in the next one. So we'll talk about it then.